Today's lesson is going to be quadratic equations.
4.5. I hope you guys recognized who that was.
Hi, this is Mrs. Crotty. Bonjour la classe.
We're going to apprendre l'équation quadratique aujourd'hui en français. Merci. La section 4, 5. Just kidding, guys. We're going to do this in English. So we're learning quadratic equations, and that's section 4.5. 4.5. So, and I don't know if you noticed, but I'm going with the Khan Academy sort of theme, trying to be Khan Academy like over here. See if it brings me any luck. So, everything that we learned in 4.4 is going to be utilized now. In 4.4, we had quadratic expressions, now we have quadratic equations. So all that we're doing is that we're adding an equal sign. We are going to be solving the following throughout. This is incredibly important. We're going to have the following: ax squared plus bx plus c, right? Our quadratic standard form. But now we're adding the following: equals 0. We're trying to find where this is true. Now, if I had just replaced the following, plus bx plus c for y, essentially what we're doing in this entire section is finding out when y equals 0. Now let's go to a graph. Where does y equal 0? Let's say I have the following: y equals 0 here and here. These are called my x-intercepts. X-intercept. So what we're finding in this section, anytime we're setting something equal to 0, when I set something equal to 0, I am finding my zeros, which is what we talked about in the last section before we start doing factoring. We're finding zeros, okay? Remember that zeros can be real or imaginary. If you have a real 0, then it is what? An x-intercept. Okay? If they're imaginary, it will not show up in your x, y coordinate plane. So what we're solving throughout this whole section, please just keep in mind we're finding my zeros. Why? Because I am setting this equation equal to 0. And factoring will help us find our zeros. Now, a really important property of that will help us throughout is the following: the zero product property. What does the zero property do? It tells us that if A times B equals 0, then A equals 0 or B equals 0. That makes sense, right? If you're multiplying two numbers and the product is 0, then for sure, either that one of the numbers or both are 0. Okay? So throughout, this is going to help us solve, and you'll see quickly how this can be translated to factoring, right? Think of these as two factors. Either one of them is equal to 0 or the other. So let us begin. Number 1, solving by factoring. Let's go really basic here. Now, if I stop there, that's last section, but now I'm doing this, equals 0. So now, ignore the equals 0 for a second, okay? Ignore the equals 0 and just factor normally. I'm looking for factors of 6 that add up to -5. It's going to be x minus 3 and x minus 2 equals 0. Now, just to give you a little pointer here, this is one of the easiest ones to get wrong with factoring. I get this all the time. X minus 6, x plus 1. This is the easiest mistake that people make, because you say, okay, -6 and 1 add up to -5. However, does -6 times -1 equal +6? No. Okay, so just please, the first condition that you have to fulfill is factors of 6. Factors of 6 that add up to -5. And now at this point, let's go back to the correct factoring. We are essentially doing this a times b equals 0. Do you guys see that? So it's a zero property, zero product property. So instead of being a, I have x minus 3, and instead of being b, I have x minus 2. So all you do is that you set both of these equal to 0. X minus 3 equals 0, or x minus 2 equals 0, and then x equals 3, and x equals 2. Now you will eventually skip this step. Eventually you will skip this step, these two steps, because you'll just see it right away. You'll see right away that that the number that makes, essentially what you're asking is what number makes this 0 and what number makes this 0. So you see clearly 3 and 2. And those are your two zeros. Those are your two solutions. They're also called roots. Okay, they're called roots, zeros, solutions to this problem. Okay. They're also what on a graph? They are x-intercepts. Why are they x-intercepts? Because they're real numbers. I can touch 3, I can touch 2 pizzas, 3 slices. So those are your two solutions, solving by factoring. Let's do another one. 2x squared minus x equals 3. Now you see here that it is not set equal to 0. So your first task really, if it's not already, is to always set equal to 0. Okay, that is your first task, if it's not already done so, to set it equal to 0. So I go ahead and do so. And then, if you can, factor. And when you're factoring, the first step is always GCF, or to look for a pattern, right? Either difference of squares or a PST. Now, I don't have a difference of squares, obviously. I don't have a PST, so then I just go to factor with my a times c adding up to b. So a times c is -6. So I need factors of -6 that add up to -1. That's b, right? So what are the factors of -6 that add up to -1? It's not going to be 6 and 1. It's going to be a 3 and 2, a combination of a 3 and a 2. And I see it's going to be -3 and +2. The -1 is bigger because it adds up to a negative number. So then I just take the middle term, right? And I split it in 2. Again, order doesn't matter. Plus 2x minus 3 equals 0. You do GCF, right? You factor by grouping. So this is one group and that's my second group. GCF here is just x. So I'm left with 2x minus 3. GCF here is just 1. And you can write the 1 if you want, if it helps you. You don't have to, okay? I don't write it, just for now, visually. And here, that's the GCF here. So you just factor it out. And at this point, you just set them both equal to 0. So 2x minus 3 equals 0. And x plus 1 equals 0. 2x equals 3. X equals 3 over 2. X equals -1. You should have seen right away that this would be -1. This one maybe not as obvious, but if you plug in back 3 over 2 into x, 2 times 3 over 2 is 3. 3 minus 3 is 0. So both of these represent x-intercepts on a graph. And you actually have enough information to draw a pretty solid sketch of this graph. You know that the y-intercept is -3 because over here, because of this. So you can plot the -3, and then you know you have two x-intercepts. You have -1, and you have 1.5, which is 3/2. Now you know it's opening upward because of this positive coefficient. So at this point you can just do a little sketch. That's not the vertex, but it's close. and that's a good sketch. Let's do a couple more examples. Still solving by factoring. Now again, number 1, always set equal to 0. So we subtract 8x, set it equal to 0, and at this point, always, once you have set it equal to 0, try to factor. So here I'm going to find the GCF, which is 2x, and I'm left with x minus 4. Set them both equal to 0, 2x equals 0, and x minus 4 equals 0. Divide by 2 on both sides. 0 divided by 2 is 0. X equals 4, and x equals 0. What do these guys represent? X intercepts. See, let's do 9x squared equals 16. So if I set that equal to 0, I get the following. And what does that look like to you? That should look like difference of squares, correct? So that becomes 3x minus 4, 3x plus 4 equals 0, and you set both of them equal to 0, so you get 3x equals 4, right? X equals 4 over 3, or 3x plus 4 equals 0, 3x equals negative 4, x equals negative 4 over 3. This first step here was, I didn't write it, 3x minus 4 equals 0, and then I just added 4. So that's how you would solve a difference of squares. Really pretty simple. Now, this example can also be solved, and this is looking towards next section, by taking square roots. So I'm going to rewrite this. Now, if you guys realize, there is no x term here, right? Which is characteristic of a difference of squares, right? There is no x term here. So at this point, I can actually divide by 9 on both sides. And then take the square root. Now, a characteristics of square roots, I'm just going to put this on the side, is that I can rewrite them like that. So what I'll do here is that I'll take x equals the square root of 16 over the square root of 9. And here I do have to account for both a positive and the negative square root, which equals the positive and negative square root of 4 over 3, which again is our answer from before. So difference of squares, you can solve them 2 ways, and this is actually easier. But again, you can do both ways, and it's awesome to have the connection there and to realize that it all is really the same thing at the end. It's just different methods of achieving the same goal. You can also solve quadratic equations by graphing, which always works. If you realize, solving by factoring only works if you can factor, correct? Solving by graphing will always work, and all that means is that you actually graph it on xy coordinate plane and try to find the point where your function crosses the x-axis. Now, this only works for real solutions, obviously, because again, we're talking about an xy coordinate plane, so you're looking for those two. On a graphing calculator, this is really simple. So let's go ahead and do the previous example that we just had, which was 9x squared equals 16. So you still have to set it equal to 0. So we do 9x squared minus 16 equals 0. And now, by setting it equal to 0 is because we're trying to find where y equals 0. But if you plug this into your calculator, if you go to y1, and go ahead and do this right now, y1, 9x squared minus 16, And then if you go to graph, go ahead and do this, guys, right now. And then you go to second trace, which is calc, the calc menu. It's the calc menu. It's your buddy. And number 2, I believe, is 0. Yes, 2, 0. There you will see. So go ahead and do that, all of you, right now. You will see something like this, first of all, right? And then you'll see that it's a little bit past 1 on both sides. So if you do the second trace 0, they'll ask you for a point to the left, again to the left of this 0. So you pick any point up here and then a point to the right, which would be down here. Guess you don't care, and it'll give you that. It'll be -4/3. And then you do the same on the other side. Now, if you can factor, that's so much more efficient. If you can't factor, that's when graphing is really, really, really convenient and really, really useful, which actually comes into play a lot with word problems. So let's go ahead and do a word problem in which we can solve by graphing. I love these word problems because they're really, just real. So if you guys remember on the quiz, there was the example of Diego kicking a soccer ball, right? So Diego kicking a soccer ball. And a classic example is this one, which I always use, in which, let's say, Diego is standing over here and he kicks a ball, right? And he goes, and the classic one, which I will ask, is how high did the ball go? When did it reach max height? And how far did he kick it? Did he kick the ball? Now, let's color code these. So this one will be white. This one will be pink. This one will be this little light blue. So how high did the ball go? That's pretty much there, right? That's the max. And it occurs where? That occurs at y value of vertex. I hope you guys can see that, right? When did it reach the max height? When? At this point, right? Again, x is always time. X tends to be time, right? Or in this case, distance down the field, right? So this is going to be x value of vertex. Because you can say, for example, here, this is actually the soccer field, right? This is a soccer field, and this is the air. Up here this is the air. And then how far did he kick the ball? Clearly it's here. That's how far. So that would be, now what we just learned, that is your 0, your x-intercept. Now, in this case, I have 2 x-intercepts, right? I have this one when he starts and this one when it lands. So you just have to be aware of which one to pick, and that's very just common sense, okay? Chicos, this screen right here is money. Money. Okay, this is really, really important in terms of concepts. You can bet that I'm going to ask you these 3 questions on your next test or your next quiz. These 3 questions. How high did the ball go? When, or how far down the field did it reach that max height? And how far did he kick the ball? All right, so let's do another example on this. So Diego, sorry to pick on you. I used to always be the soccer player, but now since we have a soccer player in the class, so let's say that Diego kicks this is still B, okay? That the function y equals -0.03 x squared plus 1.60 x models path of soccer ball. Kicked by Diego. How far did the ball travel? How high does ball go? And when does it reach max height? Now, let's go ahead and go step by step, okay? So let's label each. Let's say that this is A, how far, B, how high, and when is C. So I want to go ahead and just draw this out, and the sketch actually helps a lot. So first of all, this is my equation up here. This is my equation up here. How do I know that the origin is going to be one of my x-intercepts? How do I know that? Because if I set this equal to 0, if I set that equal to 0, which is defined as 0, correct? I can factor out an x plus 1.6 d equals 0. That means that this equals 0 and that equals 0, right? This whole thing equals 0. So I know that one of these is going to be a 0, so I can go ahead and make that a 0. And somewhere down the road it's going to land. So this over here is going to be A. How high did the ball go? It's going to be the vertex, B, up here, right, along with this height. This is going to be B. And when does it reach that max height? When? Over here, C. So why did I just do this? Because I want you to understand how to translate these words into a graph. It's so important to understand how to translate the words into what it means graphically. If you just see the numbers, you're going to get lost. And it's such a rich, awesome, tangible example. Okay, so tangible. Okay, let me erase over here so that I can have more space. Can I not erase? Let's see. Hello. Okay, apparently I can't erase. So go ahead and, I mean, this is going to be in your calculator anyway. So go ahead and input that into your calculator, okay? So input this function into your calculator at y1 and try to see, first of all, the window, right? First of all, the window. If I graph this in my standard window, which is my 10 by 10 to negative 10, you'll see right away that it'll be something like this. But you'll get cut here. You won't even see the whole thing. So you know that it can't be your standard window. I know that my x min has to be 0 and my y min has to be 0, right? So I go ahead and have my x min. And have my x min as 0. My x max, I can play around with it. I would say my x max is going to be here, right? Like around where it lands. I say that it lands somewhere there. Then my x max here, I would want it just to be a little bit more. My y max here. So let's say that just reasonably, how far can someone kick a soccer ball? I don't know, 70 meters, 80 meters tops. So let's say that I'm going to put, I don't know, 75 max. My scale, my x scale, which is just my change, I'm going to say every 5. Y min, 0. Y max, how high can a ball go? I don't know, 50 meters in the air. And then my scale, I'm going to say every 5 as well. And I go ahead and I graph it, and it turns out to be a pretty reasonable window. I actually have a lot more space up here than I needed, but it works. It works. It's a little much up here. I was a little too confident with how high a ball could go, and how far as well. but hey, it works. So now that I have a reasonable window, I can go ahead and find out my vertex and my zeros. So go ahead and find out both. I'll give you a second to do that. I'm just going to just click pause, and then I'm going to write them down here. So how do I find my vertex? I found it by doing second trace max, correct? Because in this case, since my parabola is facing downwards, which I knew because my A was negative. So I found my vertex to be 26.67, comma 21.33. And I found my my zero, this is 0. Again, I already know this one is over here is 0. I found my 0 to be 53.33, comma 0. Now, I don't know if you guys realize, but when you were finding the 0, it asks you for a point to the left. You can actually keep scrolling down. Even though I couldn't see it in my window, I just kept scrolling down, and I saw that my y values were going down. Okay, so what do these mean? This number over here is how far Diego kicked the ball. So this is how far. So this is how far. This is how high, and it's the y value because y is always height. And this one over here is when max height occurred. Meaning, if Dio's kicking the ball, it took almost 27 meters down the field for the ball to reach the max height of 21.33 meters. Now, you know I'm always going to ask you about domain and range, so over here to the side, domain. What is the actual domain? So domain in this case is the distance of the soccer field, right? Just down the field. So from where Diego starts kicking the ball. So Diego starts at 0 meters away from himself, and then however far down the field the ball is kicked. In this case, the ball goes 53 meters down the field. I hope that makes sense. This is 53, and this is 0. How high? What are the ranges of the heights? Obviously 0 when it's about to be kicked, and then the highest that it goes is 21.33 meters. So that would be your range. One final problem for today is going to be something that's going to be on the homework, which is so let's do, this is number 3, I think. Solving a system. So here it says that the graphs of the pair of functions intersect, which immediately makes you think of a system, correct? There is a solution. And I'm asked to find the points of intersection. So I have to solve the system. That's basically what I have to do. So I have the following: y equals x squared minus 2 and y equals 3x squared minus 4x minus 2. Now, if you guys realize, I haven't given you these little bracket guys, these little things, okay? Which is just to make sure you guys are still thinking of this as a system without me actually telling you it is so, okay? And the homework, they're just going to tell you this. They're not going to say solve the system. So you need to recognize that the minute you hear intersection, you need to think system of equations. So I set this up as a system of equations, no biggie. They're both equal to y, so I can set them equal to each other. So I have x squared minus 2 equals 3x squared minus 4x minus 2. And that is setting them equal to each other. However, at this point, it now becomes a quadratic equation. And with quadratic equations, why is this a quadratic equation? Because it's a quadratic equation. At this point, when you have a quadratic equation, immediately, you guys should be saying this, you set it equal to 0. So I move everything to this side. Subtract x squared, I get 2x squared. Add 2, and I get plus 0. And here, easy, I can factor, correct? After set equal to 0, after you set equal to 0, right, you want to factor. That's right after setting equal to 0, if you can factor. Which here I can, so factor at 2x, that's the GCF, x minus 2. And I'm left with 2x equals 0, which is just x equals 0. And here x equals 2. You guys should be recognizing those already, right? So I'm only halfway there. I found the x values, and now I need to find the y values. So let's go ahead and plug these guys in. So obviously I'm going to pick the first equation because it's easier, so I'm going to pick this one. And again, these are my x values, correct? So I evaluate f of 0, which is 0 squared minus 2, and I get negative 2. So one of my coordinates is 0, negative 2. And then I evaluate f of 2, that's my second x coordinate, and I get 2 squared minus 2, which is 4 minus 2, which is 2. So my second coordinate is 2, 2. And that, my friends, is your solution. Those are the points of intersection between these two parabolas up here. And that concludes section 4.5. So all that I have left to say to you is happy Friday and PSD. Enjoy, guys. Have a great weekend. Be good, and I'll see you on Wednesday, and then before for Don Bosco Day.